Hello everyone, in this video we're going to talk about Laplace transform. So Laplace is a powerful technique for solving linear ordinary differential equations. So let's look at different category of differential equations so we know what we are referring to when we say linear ordinary. So in terms of linearity, our differential equation could be linear or nonlinear, and we are only caring about the dependent variable. So if I have x dot, which is another form of dx over dt, t or time would be independent variable and x would be dependent variable. So x is important for me, that would be linear. So in this differential equation that I have x dot plus, let's say tx equals 5, I have linear because this component x dot would be linear. If I have x dot times x, then that makes it nonlinear. If I have x dot squared, that would be nonlinear. But if I have a component of t squared, that's the independent variable, so that's not gonna make my system nonlinear. And then the other category is that the order of our differential equation, whether it's a first order, second order, third order, or so forth. Basically, that's the derivative. That's the first derivative, so that would be the first order, second order. So x double dot, x triple dot, that would make it second and third order, respectively. Then I have ordinary and partial. In ordinary, our dependent variable is only function of one variable. So that's why we use dx over dt. But if it's partial, then we have to use the partial sign, because in addition to, let's say, time, I have other functions as well. It could be, let's call this t prime plus partial x with respect to t. So I have multiple variable, and our dependent variable can be function of more than one independent variable. And then at the end we have homogeneous and non-homogeneous, whether we have isolated components of our independent variable or not. If at the end I have, let's say, 5t here, that makes it non-homogeneous. If it's 0, then our equation would be homogeneous. To practice, let's look at some of these differential equations and see whether we can find what category they fall in. So for A, looking at this, our system is linear. So I'm going to write here linear. I have a t squared component, but because that's an independent variable, that's not going to make our system nonlinear. The order is a second order because x double dot, so that's the second order. It's ordinary, it's not partial. And also homogeneous because I have a 0 over there. So, and if you look at the second, here that's an example of nonlinear because I have x double dot, and x is a dependent variable, so that's nonlinear. The order is again second order because I have x double dot, still ordinary, and still homogeneous. If I go to the third, part C, our function is linear. I don't have any nonlinear component. I have the first order. I don't have second order derivatives. The equation is not ordinary, it's partial. I mean, we have the partial sign, and it's non-homogeneous. And the last one, our equation is linear. I don't have any nonlinear component. Again, this t squared is not going to make our system nonlinear because that's an independent variable. I care about x dot, x double dot. These are the components that cannot be nonlinear. And then I will have, that's the second order. It's an ordinary. And it's non-homogeneous because of these t squared. So ordinary and non-homogeneous. So here our focus is solving linear ordinary differential equation, and we know what is a linear and what is an ordinary differential equation. There are different methods to solve it. The one that we are going to focus in system dynamics, in control, is Laplace method. It's a very powerful method that changes our domain from time to complex domain and makes it easier for us to represent a lot of systems. That's why we focus on Laplace. So in Laplace, in general, is solving differential equation for us, but the way it does it, it changes the time domain to a complex frequency domain. Complex, we're not talking about simple or complex, we're talking about complex numbers, so they have a real part and imaginary part. We show it by I or J, the component. So we go from time domain to the S domain. The S domain, or the frequency domain, has the advantage that we are dealing with algebraic equations. So we can add, subtract, multiply, divide. You can't really add two differential equations or subtract different differential components. You have to solve differential equation before we could do any manipulation. But with Laplace, when we change it to algebraic form, we can really add, subtract, factor. So it makes our job much easier to solve complex problems and represent complex problems. Laplace has a lot of rules. So these are just the 5 main rules, and then I will show you the Laplace tables. We have the superposition, so the Laplace of the summation would be the same as taking a Laplace and add them together. The derivative, which is very important, if you have a derivative function, you have s times the Laplace of your function minus f at 0, at time 0. That's referred to as initial condition. A lot of times we assume the initial conditions are 0, so then that's fine, but that's the main term that needs to be present. For higher derivative, that's the equation that we have, and the derivative can be a factor of n. For the case of, let's say, f double dot, so like the second derivative, we know n is 2, so we have s2 fs minus s f0 minus f dot 0. And again, f0 and f dot 0 are initial condition, initial location and initial derivative. You can think of it as displacement and velocity. For an integral, for the Laplace takes an s in the denominator. For a derivative, it took a multiplier s. For integral, denominator. And if you have a constant value, there the Laplace is not just a constant, is the constant over s. That's the common mistake I see all the time. And this is a Laplace table. I broke it down into 2 so we can see it better. It's the rule number 1 to 10. So this column is the time column, time domain, and this one is the Laplace domain. You can see if you have this form of fraction, what would be the time response of that. So we take a Laplace, we rearrange our equation, and then we take a Laplace inverse. So that's the process of Laplace inverse when you go from Laplace to time domain. And then this is rule number 11 to 23. You will have access to these tables during the exam, quiz, and any other examination. Nobody is expecting you to memorize all of that, but you should be able to understand what these are representing. Let's solve a problem so we can further practice what we talked about. We want to solve this differential equation but using a Laplace transform. So the first step is to change this differential equation to a Laplace domain. So I need to take a Laplace of the whole thing. I show it by L. I'm going to take a Laplace of this. So Laplace of y dot is s ys minus y0 plus, and that's just for the derivative component. That was for the first component. This is the Laplace of this component. And I have another component of yt would be simply ys equals 0. So if you look at it, I have ys, so I can rearrange my equation. I can write ys and then have s plus 1 equals y0. That's the initial condition. I'm interested in finding the value of ys, so I rearrange it based on ys. I have y naught s plus 1. Now I need to take a Laplace inverse to change it to a time domain. If you look at it, that's rule number 6. Rule number 6 says that if we have, I'll write it here, rule number 6. It said that if we have a fraction of 1s plus a, the time domain response of that would be e minus at. So here a for us is 1. And then in the numerator we have an extra component that's a constant value that it stays as a coefficient. So why not whatever the value is, and then e minus at, which a here is for us is 1, so that would be the value for us. Then let's go to the next problem. Here it's the same thing. We have to take a Laplace first, rearrange it, then take a Laplace inverse. So I'm gonna take a Laplace of the whole thing here. X dot is the first derivative, so the Laplace of x dot is sxs minus x0. That's just the first component, and that's the rule that you memorize. Laplace of xt is simply xs. It's not a derivative, so I don't need to include any initial condition. I don't need to include this here. Equals, on the other side, what is the Laplace of 5? Laplace of a constant number. It's not 5, it's just 5 over s. That's something that I see as a common mistake all the time. So if I factor here is s, s plus 3, let me write it here, xs would be s plus 3. Here x0 is 2, so is negative 2, I can take it to the other side, would be 5s plus 2. Rearrange it because I'm interested in finding xs. I have 5s s plus 3 equals 2s plus 3. So now that I have rearranged it and then have my interest, the dependent variable as function of s, the next thing is taking a Laplace inverse. So we need to go and refer to the rules to see how we can take an inverse and change it to a time domain. The rule that we are going to use is rule number 6. If you remember, rule number 6, I write it here. If we have s plus a, that would be e minus at. And then another rule that comes in handy here is rule number 12. That says a, if we have s times s plus a, then we have 1 minus e minus at. Pay attention, in rule number 6, the numerator needs to be 1. And in rule number 12, the numerator should be the same as the constant value here. So I need to form my functions so they have the same format. So if I try to change these, I have s plus 3, so I write it s plus 3. According to rule number 12, the numerator should be 3, so I can solve it. But in reality, the numerator is 5. I can't really change my fraction. I can write it in this form, but then I need to multiply it by 5 over 3. So during simplification, I'm not changing my actual function. So these two values, this fraction that I've developed here, is the same as here. I just rearrange it so I can apply the rules better. The other rule that we had was s plus a, the numerator should be 1. So this one is easy. I can just separate the two from my function. Now I go to the rule xs, xt. I write this coefficient here. And then according to the rule, I'm talking about 1 minus e minus, what is a here for us? That's 3, so 3t. Plus 2, here the rule it says e minus, again a is 3 for us. If I want to, I can simplify this equation further into xt. It would be 5 over 3 minus 5 over 3 e minus 3t plus 2 e minus 3t. So xt, this 5/3 stays here, and then I have 2, which is 6/3 minus 5/3, so it would be 1/3 minus 3t. So I solved my differential equation using Laplace transform, rearrange, Laplace inverse. So for solving, you do Laplace and then you do Laplace inverse. Both of them needs to be present.